Hello friends, so this is part 2 from the year 2024, and in the part 2 we are going to do 20 questions. And all these 20 questions are from the mains. So the first question, it states that the distance between charges plus q and minus q is 2L, and between plus 2q and minus 2q is 4L. The electrostatic potential at point P at a distance r from the center O is minus alpha QL upon r square into 10 to the power 9 volts, where the value of alpha is. So basically, we are given two dipoles. Okay, one dipole is of minus q and plus q, and the distance between them is given as 2L. And another dipole is of plus 2q and minus 2q, and the distance between them is given as 4L. But both dipole, you can say, are opposite. Okay, so it means and we have to find out electrostatic potential because of both the dipoles, such that the middle point of this entire setup is making an angle of 60 degree with the radius vector or distance vector that is given as r. So in this case, first of all, let's find out the other angle. So this angle will be over 120. Okay. And here we are going to first of all find out because of the only dipole which consists of minus q and plus q. And then secondly, we are going to find out because of plus 2q and minus 2q. Okay. So we start with the first part. So we can say potential at point P due to first is plus q and minus q dipole. Let us call that potential as VQ, and this VQ is our K, P, and we have cos of theta divided by our radius square. And P is our dipole moment, and in this case that will be equal to Q multiplied by 2L. So we simply substitute it, we get our VQ is equal to K upon R square. P comes as Q multiplied by 2L, and we have this as cos of 60. Cos of 60 is 1 by 2. So we substitute the value, we get this as K upon R square, Q 2L, and multiply by 1 by 2. Here 1 by 2 and 1 by 2 cancels out. So we get this as our potential at P because of our dipole plus and minus Q will be coming as K upon R square and Q multiplied by L. Similarly, we can find out because of the dipole, that is our plus 2Q and minus 2Q dipole, and let us call that as V2Q, and that will be equal to our same formula. So we can say this will be over K upon R square and P is over here 2Q multiplied by 4L. 2Q multiplied by 4L, and the angle is cos of 60. Sorry, cos of 120. And which will be giving us minus of 1 by 2. And so we can write that V of 2Q will be equal to our K upon R square. This comes as 8QL and minus of 1 by 2. And this goes by our 4. So we get this will be equal to our minus K upon R square, and we are left with only 4QL. Now we can just find out net potential by using the algebraic sum. So we can say net potential at point P, net potential at point P, we call that as Vp, and that will be summation of our Vq and V2Q. Vq is our K upon R square, and this we have QL minus K upon R square, and we have 4QL. And now it's quite easy. We can just take common, so it comes as 1 minus 4, that will be over minus of 3. So we get our Vp will be equal to minus of 3, and this comes as QL upon R square, and value of K we can substitute, that is our 9 into 10 to the power 9. This gives us minus of 27, will be our QL R square into 10 to the power 9. And the standard equation that is given to us is our minus alpha QL upon R square. So we simply compare it with minus of alpha. This is our QL upon R square into 10 to the power 9. So we get the value of alpha is our 27. So value of alpha is our 27. There is another way also. We first of all can find out the, we can say, the net dipole, and so we can just sort it out, and we can call this in this direction. There will be our, let us suppose, P1, which will be our 2QL, and on the opposite direction we are going to have, let us suppose, P2, and that will be 8QL, and the net because of these two will be giving us, because they are opposite direction, so we are going to get the 6QL. So using this we can also find out. Okay. And obviously its direction will be towards left, so we have to use the angle as 120. In this case also we are going to get the same answer. Next question. It states that two identical charged spheres are suspended by strings of equal lengths. The string make an angle theta with each other. When suspended in water, the angle remains same. If the density of the material of the sphere is 1.5 gram per cc, the dielectric constant of water will be, take the density of water as 1 gram per cc. Okay. So in this case it states that the important part is that the angle should remain same. So we can just draw an approximate figure for that. And suppose this is the point, this is a vertical position, and we have, they are of identical charged, so because of that there will be some force of repulsion between the two, and strings make angle with each other is theta, so this is angle given as theta. So obviously there will be force of repulsion F in this direction, and other will be also F, and in the downward direction we are going to have mg, and here also we are going to have mg. Okay, and there will be tension in the string, and that tension is T. Okay. And it says that angle made, string makes angle theta with each other. Okay, so the angle with the vertical will be our theta by 2. And so we have to remember here that if theta is to remain unchanged, theta to remain unchanged, the horizontal, and which is our electric force or force due to electric, which is represented F, and the vertical force, that is our gravitational minus the buoyant force, this ratio should be same both in air as well as water. Okay, so we have to remember that. So you can say theta to remain unchanged, the horizontal, which is our electric force, and vertical, and that vertical will be our gravitational minus buoyant. Gravitational minus buoyant force ratio remains same in air and water. So only difference will be in the air there won't be any buoyant force, okay, but the ratio is going to remain same. So we can just divide into two parts. First we are going to consider in the air, and then we are going to consider in water. So let us start with our air. So we can say in air we are going to have weight, let us suppose that is given as W, which will be equal to mg, and we are going to have electrostatic force, let us call this as Fe, which will be equal to our 1 upon 4 pi epsilon naught, and we have this as Q square and R square. And so in this case this theta much better, because this theta is not going to affect, it is ultimately going to cancel. So I think best option would be that to take this theta as 2 theta, so that this angle becomes theta. Okay, no doubt in the question it is given theta, but to simplify the calculation we can just take it 2 theta. So because of that this angle will be also theta, so we can divide, our tension will be here T, and this will be a sine of theta, and here we get T cos of theta. Okay. And so we can say that horizontal force balance we are going to get our electric force will be balanced by our T sine of theta. And next is our vertical force balance. Vertical force balance, which gives us that our mg is equal to T cos of theta. So we can just simply divide them, which gives us that our T sine of theta divided by T cos of theta is equal to our Fe upon mg. Here T and T goes away, so we get this as tangent of theta will be equal to our Fe upon mg. Now we are going to find out in water. So buoyant force will be equal to the volume density of the liquid, that is water, multiplied by G. So because of this buoyant force, the effective weight will be equal to mg minus the buoyant force, that is our volume, and multiplied by G. And mass we can also write in the form of our density. So we get our effective weight will be equal to volume into G, we can take common, and we get the density of the solid minus density of the liquid, which is our water in this case. Now in water we are going to find out the electrostatic force. Electrostatic force, let us call that F prime, which will be equal to 1 upon K 1 upon 4 pi epsilon naught and our Q square upon R square. R will be same because the theta has to be same, or in this case 2 theta we have assumed. So this entire thing is nothing but our F. So we can say this will be equal to our F upon K. So simply we can write now tangent of theta directly in water. So you can say tangent of theta is basically our electrostatic force, that is our F upon K, which is here we have, let us call this as Fe, and sorry here also Fe. So this comes as Fe prime divided by and mg. Here net weight is our mg, we just found out is our Vg, and this is density of solid minus density of the water. And we just substitute our Fe prime. Fe prime is Fe upon K divided by, and this comes as Vg rho s minus rho w. And because angle has to be same, so tangent theta and this tangent theta should be same. Let us call this as equation number 1, and this we call as equation number 2. So we can say from 1 and 2, from 1 and 2, we can write our Fe upon mg is equal to Fe upon k Vg rho s minus rho w. And our Fe cancels away, G and G also goes away. So from here we can say that our K, which we are supposed to find out, will be equal to m upon V density of the solid minus density of the water, that is liquid. And mass we can also write once again in terms of the volume. So you can say K is equal to, we get this as density of the solid multiplied by its volume, and volume rho s minus rho w. This V and V goes away, so we are left with this as rho s upon rho s minus rho w. This is the dielectric constant, and the values are given to us. We simply substitute it. This is our 1.5, and here get 1.5 minus 1. So we get the value of K will be equal to 1.5 divided by 0.5, which gives us 3. So the dielectric constant of the water is our 3. Next question states that C1 and C2 are two hollow concentric cubes enclosing charges 2q and 3q respectively, as shown in figure. The ratio of electric flux passing through C1 and C2 is. So in this case we are directly going to use the Gauss theorem, and C1 is our internal cube, C1, and C2 is our external cube, and Gauss theorem is our total charge enclosed. So C1 is enclosing only 2q, whereas C2 is enclosing 2q plus 3q, that is total 5q. Okay. So we can say that C1, which basically is our inner cube, encloses q, and we have C2, which is our outer cube, and it encloses 2q plus 3q, which comes as 5q. And for C1, let us say the flux is phi1, and for C2 let us say the flux is phi2. And from Gauss theorem, we can say for C1, Gauss theorem, you know that a flux is equal to charge enclosed and divided by epsilon naught. So we can say for C1, that is our phi1 is equal to charge enclosed, in this case is 2q, so it comes as 2q upon epsilon naught, and for C2, that is our phi2, it comes as 5q upon epsilon naught. We have to find out ratio of C1 upon C2, so we get our phi 1 upon phi 2 will be equal to 2q upon epsilon naught and divided by phi q upon epsilon naught. Q epsilon naught cancels out. So this comes as 2 upon 5. So option 1 is correct. Correct. Next question. It states that suppose a uniformly charged wall provides a uniform electric field of 2 into 10 to the power 4 Newton per coulomb normally. A charged particle of mass 2 gram being suspended through a silk thread of length 20 centimeter stayed at a distance of 10 centimeter from the wall. Then the charge of the particle will be 1 upon square root of x microcoulomb, where the value of x is. So for the given, we can just draw an approximate figure. Suppose this is a wall and it's a uniformly charged wall, and it says that electric field is normal. So let us suppose we have a positive charge and a charged particle is connected with thread. Let us suppose this is its equilibrium position, and in the downward direction we are going to have our mg, and towards right, because electric field, let us suppose, is in this direction, so towards right it is going to have a force because of this electric field. Let us suppose that Fe, which will be nothing but our q times E, and this distance is given to us as 10 centimeter, and the length of this silk thread is given as 20 centimeter. So we assume this angle is given as theta. We have to find out the charge on the particle. And the force, or we can say tension in the thread, let us suppose is given as T. So we can just find out our theta. So we can say the sine of theta will be equal to 10 upon 20, which gives us that theta is our 30 degree. And if theta is 30 degrees, so this angle will be also theta. Let me draw it here. So this is mass, downward direction we have mg, towards right we are having our Fe, and tension is thread is given as T. So this angle will be also theta. So we are going to have force as T cos of theta, and this force will be our T sine of theta. And in equilibrium, vertical and horizontal forces are going to balance out each other. So we can see at equilibrium, vertical we can say our T cos of mg is equal to T cos of theta, mg, and we can say the horizontal we get our T sine of theta is equal to our Fe. So here we can just divide them and we get tangent of theta. So we can say our sine theta t sine theta upon t cos of theta is equal to over Fe upon mg. Here t and t goes away, so this gives us as tan of theta. Fe is our nothing but q times electric field, so this comes as q times E, and we have this as mg. We need to find out our charge, so we can just adjust the equation, and we get this as q is equal to mg tan of theta and divided by electric field, and all the values of we know, so we simply substitute it. We get this as 2 into 10 raised to power minus 3, g is about 10, and we have tangent of 30. Electric field is 2 into 10 raised to power 4. Tangent of 30 is 1 by square root of 3. So this will be giving us 1 upon 10 raised to power 6 square root of 3. Okay, and we need in this microcoulomb, so we can say our charge q will be equal to 1 upon square root of 3 microcoulomb, and the given value is our 1 upon square root of x. Therefore we make a comparison, and this gives us that the value of x is equal to 3. Okay, see, microcoulomb. So value of x is our 3. Next question. It states that an infinite charge sheet of uniform surface charge density sigma, which is given as 2 lambda, is situated in xy plane, and infinite long wire of linear charge density lambda is placed at 0, 0, 4 parallel to the sheet. If the net electric field is, so we have to find out the net electric field at 0, 0, 2. So we can just draw an approximate figure. So we are given that we are having a sheet. So let us put this over x-axis, this is z, and let us call this as y, much more easier. So we call this as y, and this is our x-axis. We have a sheet which is in xy plane. So this is a sheet and is in xy plane. And long wire is placed at 0, 0, 4. So let us suppose this is the point 0, 4, and long wire infinite. So this is infinite long wire. Charge density is given as lambda, and sheet surface charge density is given as sigma. We need to find out the electric field at 0, 0, 2. So we have to find out the electric field, which is somewhere here, that is 0, 0, 2. So basically we are having a sheet as well as a wire, and their relationship is given. So we can just easily find out that its surface charge density relationship is given, and the point is also given. So we can find out the electric field at, let us suppose this point is our P. So we say electric field due to infinite sheet at point P. We already know the formula. Electric field due to sheet is equal to our sigma upon 2 epsilon naught. And sigma relationship with respect to lambda is given to us, which is 2 lambda. So we substitute 2 lambda upon 2 epsilon naught. 2 and 2 goes away. So this comes as lambda upon epsilon naught. Okay. And in this case, the value of sigma is our positive, that is greater than 0. Therefore, the field will be along plus z direction. Okay. And next is because of line charge. Due to line at point P. Okay. And this point P is at 0, 0, 2, so the distance will be equal to 2. And we know that our electric field due to wire, we call this as E wire, and this E wire will be equal to lambda divided by 2 epsilon naught and multiply by R. Here R is equal to our 2. And here wire is our positive, so we can say our electric field due to wire, that is our E wire, will be equal to R is our 2, so this comes as 4 pi epsilon naught, and the point is below the wire, and the wire has a positive charge, so the field is going to point away from that is in negative z direction. So we can say in minus z direction. So net electric field that is our E net will be equal to, we get this as lambda upon epsilon naught minus lambda upon 4 pi epsilon naught z unit vector rather, and we can just take it common or we can just leave it. So we get electric field net will be equal to lambda upon epsilon naught, and this comes as 1 minus 1 upon 4 pi, and we have this as z unit vector. So this is the net electric field. Next question. It states that an infinite plane sheet of charge having a uniform surface charge density of sigma s, this should be centimeter square, is placed in xy plane. Another infinite long line charge having uniform linear charge density plus lambda e is placed at z is equal to 4 meter plane and parallel to y-axis. If the magnitude value sigma s is equal to 2 lambda e, then at point 0, 0, 2, the ratio of the magnitudes of electric field values due to sheet charge to that of linear charge is given as pi multiplied by square root of n ratio 1. Then the value of n is. So this question is almost same to the previous one. Only difference is that here we have to find out ratio, make a comparison that ratio with this given ratio and find the value of n. That's the only difference. And rest of the figure and everything will be same. So we can just write the formula that electric field due to infinite sheet, and that formula of E sheet will be equal to sigma s upon 2 epsilon naught, and direction will be positive z unit vector. Okay. And next is our due to line charge, so we can say our electric field due to line is equal to lambda E upon 2 pi epsilon naught multiplied by r. Here r is the perpendicular distance and the line is given as z is equal to 4, so value of r will be equal to 2. So we get this as E of line will be equal to lambda E divided by 4 pi epsilon naught. And now we can just find out the ratio. Okay, and ratio, we have electric field due to sheet, electric field due to line, and sheet is our sigma s upon 2 epsilon naught, and line is our lambda E divided by 4 pi epsilon naught. Here epsilon naught cancels out, and this 2 goes with 2, and we are left with will be equal to this will be our this go above, so we come this as sigma s multiplied by 2 pi divided by lambda E, and we are given that sigma s is equal to twice lambda E. Sigma s is twice lambda E, so this becomes twice lambda E multiplied by 2 pi and divided by lambda E. Lambda E cancels out, so this comes as is equal to 4 pi, and the given ratio is our pi square root of n is to 1, and this ratio is nothing but is to 1. And from here we can say square root of n is equal to 4. Square root of n is equal to 4, which gives that value of n is equal to 16. So value of n is equal to 16. Next question. We are given a charge q is placed at the center of one of the surfaces of a cube. The flux linked with the cube is. So this is a little bit tricky, not tricky, but in the sense that obviously we want to use the Gauss law. But Gauss law is about the enclosed surface, the charge enclosed by the Gaussian surface, but it says that the charge is placed at the one of the surface of the cube. So which basically means that if we have a cube, which is something like this, and suppose the charge is placed somewhere here, which is Q, and if we want to use our Gaussian law, we have to enclose this surface, and for that what we do, we draw a symmetric surface which in this case is similar to that of cube. Okay. So here we draw a symmetric surface which is similar to the cube. And something like this. So now we take a Gaussian surface which is inclusive of this entire thing. So now we are having a Gaussian surface in which the charge has been enclosed. So we can say, as per Gauss law, flux associated is our charged enclosed and divided by epsilon naught. And here the charge enclosed is our Q. You can say our charged enclosed is our Q, and this flux will be now, because of the two surfaces, so this will be also phi and this will be a phi. So ultimately we are going to get this as 2 phi is equal to Q upon epsilon naught. So the flux associated with the original, that is our you can say this surface, the original surface, will be phi is equal to Q upon 2 epsilon naught. So this comes as option number 2 is the correct one. Option 2 is correct. So here we have to remember this symmetric surface can be, you can say, mirror image of the original surface that is given to us. Here in this case was cube. Okay, and also depends upon the position of the charge. Okay. So we have to draw symmetricity so that the charge is enclosed inside the Gaussian surface. So that is the basic premise of this particular question. Next question. It states that a parallel plate capacitor of capacitance 12.5 picofarad is charged by a battery connected between its plates to a potential difference of 12 volt. The battery is now disconnected and a dielectric slab with 6 is inserted between the plates. The change in the potential energy after inserting the dielectric slab is. So here we are given a dielectric constant that is 6. So basically this question we can divide into two parts. In the first part we have our capacitor and that is connected to a battery source. And obviously that is going to charge. Let us suppose that charge is given as Q. And in the second part, the battery is removed, which is having a voltage source V. So this is also going to have voltage source V. In the second part, the battery is removed, but inside it is filled by a dielectric and here the dielectric constant is given to us, which is having a constant of 6. Okay. And as there is battery is removed, so the charge is going to remain constant. So charge in this case also will be our Q. Okay. And we have to find out the change in potential energy. So we are going to find out this is our initial condition. So this is our initial and this is our final. So let's find out the initial energy and initial potential energy. potential energy, let us call this as U naught, is equal to half C naught multiplied by V square. And all the values are known to us. We simply substitute it. We get our U naught is equal to over half C naught is given to us as 12.5 picofarad, 10 to the power minus 12. Voltage is given to us as 12 volt. So this comes as 12 whole square. So we get our initial is equal to coming as 9 into 10 to the power minus 10 joules. And the charge is going to remain same. So we can find out a final. So we can say charge remain constant. Remains constant. Therefore we can say our Q is equal to C naught multiplied by V. And okay, let me find out charge, initial charge, much more easier. So here we are going to find out our charge, that Q is equal to C naught times V, and we have this as C naught is 12.5 into 10 to the power minus 12. Voltage is given to us as 12. So we get our charge Q is equal to 150 into 10 to the power minus 12 coulombs. So charge is going to remain same. So in this case, the charge our Q will be the same, that is 150 into 10 to the power minus 12. And new capacitance, let us call that as C prime. So here the capacitance over C naught, and here capacitance, let us call this as C prime. So we can easily say our C prime will be equal to dielectric constant multiplied by C naught. Dielectric constant is given 6 into 12.5 into 10 to the power minus 12. So we get this as C prime will be equal to 75 into 10 to the power minus 12 farads. We can find out our final energy. So we can say our final potential energy, which is our suppose U naught prime, or let us call this as U prime only. U prime will be equal to Q square upon 2C prime. Q we know, so we substitute the value. We get this as 150 10 to the power minus 12 whole square 2 into 75 into 10 to the power minus 12. So we get our U prime is equal to 1.5 into 10 to the power minus 10 joules. So we have initial energy as well as we have final energy, and we have to find out the change in potential energy, so we can just subtract them. So you can see change in potential energy. Change in potential energy is our U naught minus U prime, which is our 9 minus 1.5 into 10 to the power minus 10. And this will be coming as 10 to the power minus 12. Okay, so we can just change it. This will be coming as 7.5 into 10 to the power minus 10, which gives us 750 into 10 to the power minus 12. So this is our joules. So we can make a comparison, and this we get as 750 because 10 is to the power 7, 12 is already there. So this comes as 750. Next question. It states that a rod of length 60 cm rotates with a uniform angular speed 20 radian per second about its perpendicular bisector in a uniform magnetic field of 0.5 Tesla. The direction of magnetic field is parallel to the axis of rotation. The potential difference between the two ends of the rod is. So we are given a rod. Let us suppose this is a rod, and we have two ends. Let us suppose this end is A and this end is B, and it rotates about the perpendicular bisector, that is a midpoint. Let us suppose this is a midpoint. Okay. And the magnetic field is parallel to the axis of rotation, so magnetic field is, let us suppose, inside. Okay. And it is rotating in this direction with the angular velocity of omega. And we have to find out the potential difference between the ends. Okay, so if this is our VA and this is our VB, so we have to find, we are only interested in magnitude. We can say, just say VA minus VB. We are going to find out. Okay. And the linear velocity of this will be also V, and it will be rotating in this will be also V, which is equal to omega r if r is the distance. And here also this will be r, so we get V is equal to omega times r. The direction will be opposite with each other. And because nothing as such about the, okay, for the sake of convenience, let us say that our magnetic field B is given as our B naught, and let us suppose that is in our Z direction. Okay. So the force, or we can say, because it will be rotating, so the Lorentz force acting on the rod, so we can say Lorentz force, which is our F, is given as Q, and we have this as V cross B, and here Q is obviously charge, and that will be our electrons. So we can say our F will be equal to minus E, and this comes as V cross B. And it will be trying to rotate in some kind of circular path, and V will be tangential to the circular path. And we can assume that in the one direction the velocity will be in positive y. Okay, so let me write it here only, and let me make it more clear. It is, so here the potential is VA. So in this direction we have velocity V, and the direction we have our minus of y unit vector, and here the direction will be our V, and that is our plus y unit vector. Okay, and this will be our omega times r, here also omega times r. And therefore we can say that for point B, we can say our V cross B will be equal to this. We have V unit vector Y and cross B our Z unit vector, and we get this will be equal to VB, and we get this as our X unit vector. Similarly, we can do for point A. For point A, let's do the for point A. We get this as minus V Y unit vector, and we have this as cross Z unit vector, which gives us minus V B X unit vector. And for point B, we can find out the force, that is our FB will be equal to minus E VB X unit vector, and for point A, we can say our FA will be equal to plus EVB X unit vector. And because of these forces, there will be charge separation, and from the right half, the electrons will be pushed toward the center, leftward rather, toward the center, and from the left half, it will also push toward the center. So it means the electrons will be at the center and the end will be our positively charged. So we can just easily find out the potential difference. So we can say the EMF induced in the right half will be equal to our 0 to L by 2 with respect to the center. So this becomes a P omega R multiplied by dr, and R is our L by 2, integration. So this will be coming as R square by 2, and we can write this as B omega L by 2 whole square divided by 2, which gives us B omega L square upon 8. Similarly, we can find out of the left side also, which will be equal to over minus L by 2 to 0, which comes as omega R times dr, and that will be also equal to our B omega L square upon 8. And we know that the cross product of V and B is in the opposite side. So therefore, the sign of this EMF will be also opposite. Okay. So we can say that for the left, it will be negative, and for the right, let us suppose it is positive. So total EMF E total will be equal to summation because of left plus summation because of the right. Magnitude are same, direction only the sign is different. So this comes as plus B omega L square by 8 minus B omega L square by 8, which gives us is equal to 0. And potential difference will be equal to 0. Okay. And so therefore option, there is no option, so it is our 0 volts. Next question. It states that an electron rotates in a circle around a nucleus having a positive charge Ze. Correct relation between the total energy E of the electron to its potential energy. total energy to its potential energy we have to find out. And total energy will be equal to kinetic energy plus potential energy. And we already know the relationship between the kinetic energy with respect to potential energy. So we can say that the total energy is given as our E, which will be equal to our kinetic energy plus potential energy, that is given as U. Okay. And for a circular orbit, we already know that our, so you can say for circular orbit, our kinetic energy is equal to -1/2 of the potential energy. So we simply substitute it. We get our energy E is equal to -1/2 U plus U, which gives us U upon 2. And this gives us that the U is equal to 2 times E. U is equal to 2 times E. Option 4 is correct. Option 4 is correct. Next question. We are given 3 capacitors of capacitances 25, 30 and 45 microfarad are connected in parallel to a supply of 100 volt. Energy stored in the above combination is E. When these capacitors are connected in series to the same supply, the energy stored is 9E by X. So we have to find the value of X. So we have two configurations. First configuration, all these capacitors are in parallel. So let us call this as C1, C2 and this is C3. So first we have all these in parallel. This is C1, C2 and C3. C2 and C3, and they are connected with the supply voltage. Let us suppose that voltage is our V, which is our 100 volt. And in the second case, all these are connected in series. So for series, so this is our C1, C2 and C3, and they are connected with the same supply voltage, that is our V, which is our 100 volt. So we have this as C1, C2 and C3. And for parallel, let us suppose the equivalent capacitance is given as Cp. So this Cp will be equal to C1 plus C2 plus C3. So we substitute the value, we have this as 25 plus 30 plus 45, which gives us 100 microfarad. We can just find out energy in parallel, that every EP, in this case it is given as E, will be equal to over half Cp V square, and this comes as our half Cp is of 100 into 10 to the power minus 6. Voltage is given as 100 square. So we got our E will be equal to our E is equal to 0.5 joules. Similarly, we are going to solve for the series also. So we can say for series it has to be 1 upon Cs. 1 upon Cs is equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3, which gives us 1 upon 25 plus 1 upon 30 plus 1 upon 45. And the Cs will be approximately equal to 10.47 microfarad. And this series energy, we call this as ES, will be equal to 1/2, and we have this CS and V square. Voltage is same, so we get this as energy in the series is equal to our 1/2 into 10.47. Voltage is about 10 whole square, which gives us that the series energy is approximately equal to 0.05, and this comes as 235 joules. And the relationship is given to us. We are given that our ES is equal to 9 times E divided by X. So we substitute the values. ES is our 0.05, 23 is equal to 9 times E, and E is our 0.5, and divided by our X. So we get that our X is equal to 9 into 0.5, and the 0.0523. So our X will be approximately equal to 86. So value of X is our 86. Next question. It says that sigma is the uniform surface charge density of a thin spherical shell of radius r. The electric field at any point on the surface of the spherical shell is. So it is directly based on the, you can say, Gaussian one. And for that, let us consider a spherical shell, and in this shell we consider a small surface, Gaussian surface, and its area is, let us suppose, given as dA. Obviously the electric field will be perpendicular to this point, and inside of the shell the electric field will be equal to 0. So we can say by Gauss law, over a closed surface for area dA is equal to over charged enclosed upon epsilon naught. Surface charge density for is given as sigma, so this becomes sigma multiplied by dA upon epsilon naught, and our left side will be our E into dA is equal to sigma dA upon epsilon naught. dA and dA cancels out, so we get our electric field is equal to sigma upon epsilon naught. So we have our option 3 is the correct one. Option 3 is correct. Next question. It states that 3 infinitely long charged thin sheets are placed as shown in figure. the magnitude of electric field at point P is x times sigma divided by epsilon naught. The value of x is. So we are given three sheets placed at -a, +a and +3a, and point P is given somewhere here. And we have to find out the magnitude of electric field at this point P. In this case, we have to remember, there's in case of thin sheet, the distance between the plate and the point doesn't matter. Okay, it's independent basically. Okay. So we can say that electric field due to infinite plane sheet is independent of distance. Is independent of distance of the point from the sheet. So we can just use the superposition principle, algebraic sum. We are going to get net electric field. And the formula for electric field due to the sheet is given as sigma upon 2 epsilon naught. And depending upon sigma, whether there is a positive or negative, we can just find out the direction. So we can say if our sigma is positive, that is greater than 0. So in this case, the direction will be away from the sheet. And if we have our sigma is less than 0, then it will be toward the sheet. So first is, let us suppose at x equal to -a, let us call this as sheet 1, this is our sheet 2, and this is our sheet 3. So you can say for sheet 1, which is our S1, in this case our x is equal to -a, and sigma is given as minus of sigma, and point P is the right of the sheet. So we can say point P is right of S1. So our E1 we get with a sigma 1 and divided by 2 epsilon naught, which gives us sigma upon 2 epsilon naught, and direction will be left. Similarly, we can find out for sheet 2, that is our S2, and it is placed at x is equal to a, and our sigma is our -2 of sigma. So point P is still in the right, and we can just find out our E2 will be equal to twice sigma twice epsilon naught, giving us sigma upon epsilon naught, and direction will be towards the left. Finally, sheet 3. For sheet 3, that is our S3, we are having x is equal to over 3a, and sigma is given as plus sigma. So we can say our E3 will be equal to sigma upon 2 epsilon naught, and point P is left. Point P is toward the left, so the direction will be towards left. So total field at P, let us call that EP, will be equal to E1 plus E2 plus E3. We simply substitute the values. We get EP is equal to sigma upon 2 epsilon naught plus sigma upon epsilon naught plus sigma upon 2 epsilon naught. So this comes as LCM will be 2 epsilon naught, and it will be coming as sigma plus 2 sigma plus sigma, which comes as 4 sigma upon 2 epsilon naught, giving us twice sigma upon epsilon naught. And we are given that it is x sigma upon epsilon naught. So we are given that x sigma upon epsilon naught is equal to 2 sigma upon epsilon naught. This gives us that value of x is equal to 2. So value of x is equal to 2. Next question. It states that two identical conducting spheres P and S with charge Q on each repel each other with a force of 16 Newton. A third identical uncharged conducting sphere R is successfully brought in contact with two spheres. The new force of repulsion between P and S is. Okay, so we are having initially two spheres and uncharged sphere is R. Okay, so here we can say that initial force between P and S, initial force, which will obviously repulsive because it is given in the question, initial force, let us call this as Fi, will be equal to, it is given as 16 Newton. And if we assume that charge on P and Q, they carry a charge of Q, sorry, P and S. You can say charge on P and S each is, let us suppose, given as Q. So we can say force Fi will be equal to K Q square and R square, which will be equal to 16. Now it is said that an uncharged sphere is brought in contact with two spheres. Okay, the order is not given how they are brought in contact. So let us first assume that R touches P, and remember R is initially uncharged. Okay, so therefore you can say R is uncharged, but it is given as it is identical to P as well as our S. So because of that we can say that charge will be equally divided between P and R. Charge will be equally divided between P and R. So therefore, new charge let us suppose that is our QP prime, which will be equal to QR prime is equal to Q upon 2. And now sphere R touches sphere S. R, now it is having a charge of Q by 2, it's not uncharged, touches S, and S is having a charge of Q. So therefore, the new charge, let us call this as Q, much more QR, okay, because QR prime we can use later on. So it touches S, which is having a charge Q. So we can say that new charge which will be our Q prime S will be equal to our Q prime R will be equal to Q plus Q by 2 divided by 2, which comes as 3Q divided by 4. We can just use the potential method also, but it will be a little lengthy. We can just find out the charge because everything is identical about the spheres. So final charge on P, that is our Q prime P, is equal to Q by 2, and on our R, sorry, not R but S, is our Q prime S is equal to 3Q upon 4. So final force between P and S. Final force between P and S, let us call this F final. So we can write our F final will be to K, and charge is our Q by 2 multiplied by 3Q by 4, and this is our R square. So we can write this as 3 by 8. And this comes as K Q square upon R square. And this value is given to us as 16. So we can say this as 3 by 8 multiplied by 16. And this goes by 2. So we get our F final will be equal to 6 newtons. So option number 2 is correct. Option 2 is correct. Next question. It states that a capacitor of 10 microfarad capacitance whose plates are separated by 10 mm through air and each plate has an area of 4 cm square is now filled equally with two dielectric media of K12 and K23 respectively as shown in figure. If new force between the plates is 8 Newton, then the supply voltage is. So basic figure is given to us. We are having two dielectric K1 and K2, respective values as 2 and 3, and distance between a plate is given as D. So this question is, you can say, a little bit tricky, and there was, you can say, difference in the answer that is mentioned by NTA and the solution provided by the one of the, you can say, many persons. So I'll try to, I'm not sure whether this approach will be correct one. Hopefully it is correct, because that is going to give us an answer and that matches with the NTA. So hopefully this approach will be beneficial. Okay. So initially we are given that we have a capacitor, and let us suppose we draw the basic figure that is without dielectric. Capacitance is given as C0, and area of the plate is, let us suppose, A, and distance between the plates is D. Okay, so everything is given to us. So we can write that without a dielectric, we can say our C0 will be equal to epsilon naught A upon D. So from here we are going to find out value of epsilon naught, because C0 is given to us 10 microfarad. So this gives us 10 10 to the power minus 6 is equal to epsilon naught. Area is given to us as 4 into 10 to the power minus 4 and divided by 0.01. So this gives us the value of our epsilon naught is equal to 2.5 into 10 to the power minus 4 farad per meter. And based on this epsilon naught, we are going to find out what will be the capacitance of each part based on their dielectrics. So we can see now with the dielectric, so K1, let us suppose this capacitance is given C1, and for K2 it is C2, and obviously the area will be our A by 2 here also, and here also area is A by 2. So with the dielectric, our C1 will be equal to our K1 epsilon naught A1 by D, and this will be giving us 2 multiplied by epsilon naught, and area is our now half, that is our 2 into 10 to the power minus 4. Distance is same, that is 0.01. And similarly we can find out our C2 will be equal to our K2 epsilon naught A2 divided by D. K2 is given as 3 epsilon naught into 2 into 10 to the power minus 4 divided by 0.01. So total capacitance, we are only talking about the with the dielectric. You can say total capacitance, that is CT, will be equal to C1 plus C2. We substitute the values and rest of things will be same. So this comes as 2 plus 3, and we have here epsilon naught into 2 into 10 to the power minus 4 divided by 0.01, which comes as epsilon naught multiplied by 10 to the power minus 1. Okay. And epsilon naught we just found out is 2.5. So we can say our CT will be equal to 2.5 into 10 to the power minus 4 into 10 to the power minus 1 will be giving us 2.5 into 10 to the power minus 5 farads, or we can say 25 microfarad. And our C naught is given to us as 10 microfarad. Our C naught, which is our epsilon naught A upon D, it is given as 10 microfarad. So therefore, we can find out our C1 will be equal to okay, so this comes as K1 epsilon naught A upon 2 and D, and this comes as our 2 upon 2, and this comes as epsilon naught A upon D, and this epsilon naught A upon D is nothing but our C naught, whose value is 10 microfarad. 2 goes by 2, and this comes as our C naught is equal to 10 microfarad. Similarly, we can find out our C2 will be equal to K2 epsilon naught A by 2 divided by D. K2 is our, so this comes as 3 by 2, and once again epsilon naught A upon D, and this factor is our C naught, so this comes as 3 by 2 multiplied by C naught, which gives us 15 microfarad. So we get our C total is equal to C1 plus C2, which comes as 10 plus 15 microfarad, giving us 25 microfarad. So one thing we have verified, that the value of epsilon naught, which is also giving us a 25 microfarad of the total capacitance, and here also we are getting the total capacitance with respect to their individual, or we can say with respect to the given capacitance of C naught, is also coming as 25 microfarad. Okay, so this approach is, you can say, going to provide us a correct answer. Now we come to the forces on the plates. Force between the plates. Force between the plates. And for parallel plate capacitor, if the force is represented as F, which will be equal to half epsilon E square multiplied by area. Okay. And since we are having two dielectric, so therefore the total force will be the sum of forces of each dielectric. And here we have to remember that of electric field E is equal to V upon D. So the force due to K1, force due to K1, which will be our F1, is equal to, this we get our 1.2 epsilon naught, this will be V upon D whole square multiplied by A1. Similarly, we can write that our force due to K2 will be equal to F2 is equal to 1 half, and this is V upon D whole square, and this comes as our A2. So total force, that is our F, will be equal to F1 plus F2. All the things will be common except the area. So we can write this as 1 half epsilon naught V upon D whole square A1 plus A2. Now we simply substitute the values. We get this as, one second. Okay, total force is given. Voltage we have to find out. So we can write this as total force is over 8. This comes as 1/2, and epsilon naught is our 0.5 into 10 to the power minus 4, and V, this comes as our V square divided by 0.01 whole square, and area is same. Okay, one second, I miss my K1, K1, K2. So this comes as K1 multiplied by K2. So we are going to get this as our 2 into 10 to the power minus 4 plus 3 into 2 into 10 to the power minus 4, because area is equally divided. Now it's quite simple to solve it. Okay. So this will be giving us 816 and is equal to 2.5 into 10 to the power minus 4, and this will be our 10 raised to power 4, and we have here 4 into 4 plus 6, that is 10 into 10 to the power minus 4 into 6, yeah, 10 to the power minus 4, and our V square. So we can just this, sorry, ten to the power minus 4, and we can cancel it. So this comes as 10 to the power minus 3 and 2.5. So we can say this will be 16 is equal to 2.5 into 10 to the power minus 3 times V square, which gives us our V square is equal to 16 upon 2.5 into 10 to the power minus 3, and 16 goes above. This comes as 16 into, this comes as our 16 and divided by 160, 25, and multiply by 10 to the power 3. So which gives us, this will be equal to V square is equal to 6400, and V will be equal to 80 volts. So we get value of V, supply voltage is our 80. Okay, so this is my take on this particular question. Next question. It states that two charged conducting sphere radii A and B are connected to each other by a conducting wire. The ratio of charges of the two spheres respectively is. So we are giving two charges of different radii, and we have to find out the ratio of charges of the two. Okay. And when they are connected, their potential has to be same. So we can say, we know the potential, that is our V is equal to our K times Q upon R. So we have two charge conducting spheres. So let us say one is our having a VA is our QA radii is our A, and other one is our VB is equal to K, and this comes as our QB upon B. And this VA and VB will be equal. We can say our VA is equal to our VB because they are connected with each other. This gives us K QA upon A is equal to K QB upon B. K and K goes away. So we get the ratio QA upon QB will be equal to A upon B. A upon B, option 3 is correct. Is correct. Next question. It states that an electric field E given as 2I plus 6J plus 8K divided by square root of 6 passes through a surface of 4 meter square area having a unit vector, n unit vector, that is 2I plus J plus K divided by 6 square root. The electric flux for that surface is, this is directly based on formula. We know that electric flux is given as our dot product of E as well as the area vector, which we can further write as EA cos of the angle between them, which is theta, and we can also write in terms of the unit vector, because area unit vector is given as n unit, so we can write this as E dot n unit vector and multiply by our A. So we simply substitute the value of electric field as well as n unit vector. So we get our flux phi is equal to 2I plus 6J plus 8K unit vector divided by square root of 6 dot n unit vector, which is 2I plus J plus K unit vector and root 6, and multiply by area is given to us as 4, so multiply by 4. So we can just find out the unit vector, which is, you can say 2I into I, J into J and K into K. So we get 2 into 2, which is our 4, plus 6 into 1, 6, plus 8 into 1 is 8. And numerator will be coming as 6 and multiply by 4. So this will be coming as 18 divided by 6 multiply by 4. So this goes by 3, giving us flux as 12. So flux will be coming as 12 voltmeter. Next question. It states that a capacitor has an air dielectric medium and two conducting plates of area 12 centimeter square, here also centimeter square, and they are 0.6 centimeter apart. When a slab of dielectric having area 12 centimeter square and 0.6 centimeter thickness is inserted between the plates, one of the conducting plates has to be moved by 0.2 centimeter to keep the capacitance same as in the previous case, the dielectric constant of the slab is. So in this case, we have to remember that as soon as the dielectric is added, one of the plate is moved. Okay. So we can just draw an approximate figure for that. And this is our initial condition. And the area is, let us suppose, A, and the distance between the plates is, let us suppose, D. Capacitance is, let us suppose, our C naught. And air is a dielectric, so value of K1 is equal to A. In the second case, dielectric slab of area is 12 centimeters. So initially, the distance between the plate is 0.6 centimeter. Okay. So initial distance is exactly 0.6 centimeter, and dielectric is also having the distance as 0.6 centimeter apart. So dielectric is going to completely fill this portion. But as soon as dielectric is added, one of the plate is shifted by a distance of 0.2 centimeter. So let us suppose that plate is moved here, and this is our 0.2 centimeter. But the dielectric is having only the distance of 0.6 centimeter. Okay. So this portion will be consisting of our air. So this will be our air, and this will be our dielectric. So air means we have, that is K1 is equal to 1, and here let us suppose dielectric constant is given as K2. Area of both are same. Okay, so area is our A. Area is not, area of the plates is same. So let us find out. This is our initial, and this is our final. So the initial capacitance that is C naught will be equal to epsilon naught A upon D multiplied by K1, where K1 is our 1 because of the air. So I can say my C naught will be equal to epsilon naught A divided by D. And the final condition, we have two dielectrics. One is our air, and another one is dielectric, which is having a dielectric constant of K2. So we can say that final capacitance and which will be consisting of our air gap plus dielectric. And let's assume that the thickness of dielectric is T. Later on we can just substitute the values. We can say thickness of dielectric is T, and the air gap is our X. Thickness of air gap is our X, and this T is having a dielectric constant of K2 and air dielectric constant of K1, which is obviously equal to 1. So therefore we can say that is our C1, that is capacitance for air capacitance will be equal to over K1 epsilon naught A upon X. K1 is our 1, so we can write this epsilon naught A upon X. C2, which is our dielectric capacitor, will be equal to our K2 epsilon naught A upon thickness is our T, and equivalent capacitance let us suppose we write this as C is equal to 1 upon C1 plus 1 upon C2. So from here, if we substitute the value, we get this as 1 upon C is equal to C1 is upon, this comes as X upon epsilon naught A plus this comes as T upon K2 epsilon naught upon A. So we can take epsilon naught A as common. So we get this as 1 upon epsilon naught A, and this will be coming as X plus T upon K2. So we get our C will be equal to epsilon naught A, and this comes as 1 upon X plus T upon K2. So this is our net capacitance, but it is given that initial and final capacitance is same. Okay, so we can say but initial capacitance is equal to final capacitance, which basically means that C naught is equal to C, and our C naught was epsilon naught A upon D. So from here we get epsilon naught A upon D is equal to epsilon naught A, and this comes as 1 upon X plus T upon K2. Epsilon naught A cancels out, and we can write this as D is equal to, or X plus T upon K2 is equal to D. We are interested in finding our value of K2, so we can say that T upon K2 is equal to, this comes as D minus X, which gives that our K2 is equal to T upon D minus X, and we know all the values. So we can say our K2, T is the thickness of the dielectric, and the thickness of dielectric is given to us as 0.006, and D is the original distance. Original distance was also our 0.006 minus X is the air gap, which is 0.002. So this comes as 0.006 divided by 0.004, which gives us 1.5, or we can say 3/2. So we get dielectric constant of the dielectric material is 3/2. Oh, it is given decimal, so option 1 is correct. One is correct. Next question. it states that if the net electric field at point P along y-axis is 0, then the ratio of Q2 upon Q3 is 8 by 5 square root of x. We have to where value of x is, which we are going to find out. Basic figure is given to us. We have charges plus Q2 and minus Q3, and we have a point P which is somewhat unsymmetrical with respect to the axis. So we can just draw the respective electric fields. So electric field, because of this Q2, is in this direction. So let us suppose we call this as our E2, and because of Q3 it will be somewhat in this direction. Let us we call this as E3. And is it unsymmetrical? So let us call this angle as our theta 1, and this angle let us call that as our theta 2. And it says that we can just divide the respective our electric fields into the component. Okay, so for that let us draw it here. So this is point P. We have a electric field of E2, and so this angle will be over theta 2, and so we can say this will be our E2 cos of theta 2, and here we are going to have our E2 sine of theta 2. Similarly, we have our E3, and the angle here is our theta 1, so this comes as our E3 cos of theta 1, and here we are going to have our E3 sine of theta 3, but it is given that along y-axis the electric field is 0. So we can just write it that along y-axis E of y is equal to 0, and we can just write it. So we get from here that our E2 cos of theta 2 will be equal to our E3 cos of theta 1. E2 and E3 we can just substitute. Okay, so we can find out the distance also. So this is 2 and 4, so 4, 16 and 4, so this comes as square root of 20, and this will be coming 16 plus 9 square root of 25. So E2 we can say K Q2 divided by our 20 multiplied by cos of theta 2 is equal to K Q1, and this is 25 and square root and cos of theta 1. K and K goes away, and we have to find out the ratio. Okay, and cos of theta 2 and cos of theta 1 we can just easily find out. So this is now it's correct. So we get this as our Q2 upon 20 multiplied by 4 upon square root of 20 is equal to Q1 upon 25 into 4 upon square root of 25. We have to find out the ratio Q2 by Q3. 1 second. This is not Q1 but Q3. Q3 and Q3. And 4 and 4 cancels, so we get Q2 by Q3 will be equal to, you can write this as 20 upon 25 multiplied by square root of 20 divided by square root of 25, and you can just solve it. This goes by 5 4, and this will be coming as 5 and this comes as 4, and it will be giving us 4 upon 5, and this is square root. Let me write the common square root, much more easier. Common square root, and this also we can just cancel out. This becomes 4 and this becomes 5, and square root of 4 will be coming as 2 and this comes as square root of 5, which gives us 8 5 into 1 upon square root of 5, and we are given it is 8 upon 5 square root of 5. 8 upon 5 into 1 upon square root of x, which we need to find out. So we can say value of x is equal to 5. Value of x is about 5. Next question. It states that an infinitely long positively charged state thread has a linear charge density sigma per centimeter. An electron revolves along a circular path having axis along the length of the wire. The graph that correctly represents the variation of kinetic energy of the electron as a function of radius of circular path of the wire is. So basically we have to find out the relationship between the kinetic energy and the radius. So for that we can just drive the relationship, and for that let us draw the circuit. Suppose this is the path and we have a wire which is infinitely long and is having a positive charge, and electron is revolving, suppose in this direction, and the radius is given as our r, and this is our electron. So we can find out electric field because there will be force acting on this electron because of the electric field. That will be our electron suppose charge into E, and this is going to provide us a centripetal force, okay, which will be our mv square upon r. So therefore we can say electric field at, let us call this point as P, and this is center O. Electric field at point P, we can write this as EP is equal to, this is our K, and charge density is given to us as lambda, so this becomes a 2 lambda upon distance, that is our r. R. And we can also say the force on the electron, that is of Fe will be equal to electron multiplied by electric field. So we get our force on electron is equal to, we have here K 2 lambda upon R. Now this force will provide required centripetal force. This force will provide required centripetal force. Which is nothing but our mv square upon r. So we can just equate them. We get our E multiplied by K 2 lambda upon R is equal to mv square upon R. And here our R and R cancels out. So we can write our velocity V is equal to, this comes as 2ke lambda divided by m square root. We need to find out the kinetic energy. So we can say our kinetic energy is equal to half m v square, which gives our half m and 2ke lambda upon m. And here m, 2 and 2 goes away. So we get our kinetic energy is equal to k lambda E. And this is independent of R. Independent of R, that is a radius. So which basically means it is going to have a constant. Option 2 is correct. Option 2 is correct. So I think this was the last one. Yes. So this was the part 2 of the questions that were asked in the year 2024, and only the main questions are covered in this 24. Okay. Remaining mains as well as advanced we will try to cover in part 3. If required, we will also do a part 4. So this completes, and in this part we completed 20 questions. So this completes all the 20 questions. Thank you.